Okay, so we're going to look at a system of two particles. Just for fun, let's do this in a couple different colors. So I'm going to put one called M1 here, and one called, well, that's not very bright, M2 here. And these particles will only be interacting via a central force between them. So that will act somewhere along this line between them. This is in a three-dimensional space. We'll have some origin out here, and we're going to have a position vector, which we're going to call R1 for this particle, and a position vector here, R2 for that particle. So their potential is going to be only a function of the distance between the two particles. And so we can see if we were to if we want to find the vector from one to the other, we just have to add, say, one of these vectors plus the opposite of the other one. So, for example, if I want to go from M1 to M2, all I have to do is take the arrowhead on this one, move it over here, so take the opposite of this vector, and then go here and then here. So it's equivalent to this vector here, vector addition. So since we just switch one of these arrowheads, it's just a minus sign, and the distance between these 2 points is just, we just subtract the 2 vectors. And I'm taking the magnitude of this, because this potential is a central force, and the potential in this case will depend only on the distance between the two. So we only need the magnitude, distance, not displacement. All right, so our question is, what is the Lagrangian of this system? So we know the Lagrangian is equal to the kinetic energy minus the potential energy. And the kinetic energy of this system, well, we have 6 generalized coordinates, which are the x, y, and z positions of this particle and the x, y, and z position of this particle. If we keep that written in vector form, we're going to have the kinetic energy of this one and this one, and we'll just get 2 terms. So we'll collapse 3 of the coordinates into one vector and 3 into the other vector, specifically R1 and R2. So we have 1/2 M1 R1, and we're squaring this. Okay, so this is just 1/2 mv squared. The r dot is the time derivative. So that's the kinetic energy of the one particle, and the other one will have 1/2 m2 r2 dot. All right, so 3 degrees of freedom here, 3 degrees of freedom here, because if I were to write out each one of these vectors, so just for example, if we write out r1 equals rx x hat plus ry y hat plus rz z hat. Okay, so 1, 2, 3, 3 here, 3 here, 6 degrees of freedom. All right, so now we'll write out our Lagrangian. We have T, we have V, and this is in general form. I mean, generally you'll get a 1 over, if we call this magnitude here, or this scalar, which is just the magnitude of this distance vector right here. Actually, this would be R2 minus R1. Yes. If we're looking at the magnitude of this vector, which we'll just call R, generally we get, in a lot of cases, you get a V equals some constant, we'll call A, divided by R. So this applies to the Coulomb force between two charged particles, or the gravitational force between two masses. But here we're just keeping it all general. So in general, it's just a plain central force. We haven't specified whether it's attractive or repulsive. The common example of 1 over R potential or some other crazy potential, we just keep it in this general form here. And so we get this T minus V, which is just what we had here. And minus this V. I'm just going to write the little r, which is equal to this this magnitude of this vector, just like we talked about. So here's the Lagrangian, written in general for these two particles in 3 dimensions, with a central force between them. All right, so now what we're going to try and do is change to a center of mass coordinate system. So rather than use the coordinates of these two, we're going to use the coordinate of the center of mass. So we need to find the relation between these this R1 and R2 that we have, and the coordinate to the center of mass. So we're going to go ahead and we're just going to use we're going to go ahead and define a vector just called R, which we've used before. The magnitude of it, it's just going to be this right here, like we talked about before. R2 minus R1. All right, now we know the center of mass, so the center of mass is going to be somewhere in between here. It depends on, if M1 and M2 are equal masses, then it will be right in between them. Otherwise, it'll be somewhere in between. But it's really just kind of a weighted average of their two positions, weighted by their masses. So I'm just going to draw, in general, a vector of this big R here to represent the position vector of the center of mass for them. All right, and the position vector, like we said, is the weighted average of the two masses. So that's M1 R1 plus M2 R2 divided by the total mass, which is M1 plus M2. All right, we're going to define this, we'll define it over here. We'll just call it a big M equals M1 plus M2, like that. So this is equal to M1 R1 plus M2 R. I'm going off the paper. R2, you'll have to use your imagination on that one. And then is over big M. So the only change I made here is just plug in big M for this. All right. All right. So now we find out if we multiply this big M over here, we get big M big R equals little m1, little r1, little m2, little r2, like that. So it's still the same system, and we still need the same number of generalized coordinates in order to describe it, one of which is this big R, so the coordinate to the center of mass. The other one is this little r right here, which is the vector of the separation between the two masses. All right, so what we're trying to do is eliminate this r1 and this r2. So if we go ahead and plug this equation in, so I'm just going to rearrange this equation a little bit and say r2 equals r plus r1. These are all vectors. Now if we plug this in here, we get big M big R equals m1 r1, that plus m2, this little r, plus r1, like that. Okay, so now we're going to try and get r1 off by itself. So let's see what we've got here. I can take this and go m1 plus m2. So I'm taking this m2 r1 term and I'm bringing it out, and then I'm recombining these two m's together. So like that, and then we still have this plus m2r, like that left over. And this is still equal to big M, big R. All right, so now we solve this for R1. So this big M, big R here, we're going to minus M2 and this R, then we divide by this part right here, M1, M2. Added together. All right, so now we have an equation for R1. We can do the exact same thing with this equation up here, and then we can get an equation like this for R2. So let's see, so I want to solve this one up here for R1 instead, which is just going to be R2 minus R. So I'll write that over here, make sure I'm still on the screen. R1 equals R2 minus R. Okay, now we plug this one into here. Plus M2R2. Sorry. Have to keep these separate. Okay, now we're going to try and solve for R2. That was our goal. So this was equal to M1 plus M2 R2 minus M1R from this term in here, and this gives us R2 equals big M big R. Make sure I'm still on the page here. Where was I? Right here. Okay. So this and then plus m1r, and then divide by the m1 plus m2. And again, this, I could have just written big M. All right, so let's clean these up real quick. All right, so here we have R1. Okay, so I'm just going to write this way. So equals big M R minus M2R. And I'm going to write this term as big M now, like this. All right, and that, if I divide this out, I get big R minus M2 over big M times little r. All right, and then same goes for R2. Okay, same story with this equation right here. I will get a big R, except now we have a plus sign here, plus an M1 over big M times little r, like this. All right, so now what we're ready to do is, now that we have our equations for R1 and R2 in terms of, again, this was the vector to the center of mass between the two. And this is the vector between the two masses. So the separation and then the position of the center of mass. All right, so now we're going to try and rewrite this Lagrangian in terms of these two new generalized coordinates, big R, little r, as opposed to R1 and R2. Okay, so what we're going to do is we're just going to plug these two expressions right into here. We're just going to leave this v in this general form, which is just dependent in some way on the magnitude of the separation between the two. Again, the most important example of that is just a 1 over r potential, or a 1 over r squared force between the two, which you find in electromagnetism and gravity, and pretty much the important cases of what you'll encounter. All right, so here we have our Lagrangian equals 1/2 m1. All right, now we need to take the time derivative of r1 and then square it. And one good thing is we know that the masses aren't going to be changing. So that's just going to be the time derivative of the big R minus M2 over big M, time derivative of the little r squared. All right, plus 1/2 M2, and now we're going to do the same thing with this one. Make sure this is all still on camera. Okay. All right, and then we can't forget our little minus the function of the magnitude of this separation vector. All right. All right, so here we go. I'm just going to do a little algebra here. So 1/2 1, okay, r dot squared minus 2m2 m. Like that, plus m2 big M. Yeah, I'm going to draw a line here so we keep this v separate from what's above it. All right, so here's the first term. And now we're going to write out the second term. Okay, and this time we have a plus. And then M1 plus m. Oh, you know what? I forgot to square those two parts. Okay, and as always, minus v function of r. All right, so we look around for ways we can maybe simplify this. One thing I see is here we have an m1 and an m2 in this middle term, and here we have an m2 and an m1. All right, so it looks like these two middle terms are going to cancel out. All right, they have different sign. Yeah, I think they're gone. Okay, so that's nice. Got that going for us, which is nice. Let's see. All right, so I'm gonna combine these two terms into an m1 plus m2, which is really just big M. All right, so that takes care of that one. Plus, let's see what we need here. We can factor out the 1/2. We can factor out the r dot squared, and we're going to factor out the big M squared. But then we have these two terms, this m1 m2 squared plus m2 m1 squared. All right, so those don't go away yet. And we have our V of R. All right, let's find a clean page. Okay, so now what we're going to do is just work on simplifying this. So our Lagrangian is equal to, all right, so I'm going to go ahead and put in the big M now. Big M. All right. All right, so now one thing we have, okay, so now we're down to, if we, let's see what we can do here. We can factor out an m1, m2 over big M squared. And then here we just have an m2 plus m1, something like that, and then minus our VR. And what we have here, we notice that this m2 plus m1, well, that's just this big M. So that will cancel out with one of them, right? So we're left with m1, m2 over big M minus v bar. All right, now, so this quantity right here, sort of a geometric mean of the two masses, is what we call the reduced mass of the system. All right, so if we factor out this 1/2, we can have big M, big R, plus the reduced mass. Oh, that's so terrible. I'll have to keep it straight. Okay, and then minus the bar. so here is the Lagrangian in our new generalized coordinates, which are much more convenient in some ways for worrying about these multi-particle systems. With our two particles here, we have one generalized coordinate, which is the, again, the vector to some point in between them, wherever the center of mass is, a weighted average of position based on these kind of the ratio of these two different masses, and then also the reduced mass of the system. All right. Okay, so battery died, but hopefully we'll have enough charge to get through this last part. All right, so now we have our Lagrangian, and we wanted to find our equations of motion from that. And what we're going to do, so here I've written the Euler-Lagrange equation, which is x is a generalized coordinate. We'll start with the big R, since it's maybe less interesting. Save little r for last. We don't see any place in the Lagrangian where big R appears without the derivative. The potential does not depend on it in this case. All right, so this term is equal to 0 in this case. All right, so what do we have? We have, all right, taking the derivative of this with respect to big R dot. We just have m big R double dot. All right, okay, so this is our first equation of motion. Well, oh yeah, sorry. There should just be one dot here. I jumped ahead of myself. Once we take this derivative of it, I'm going to ignore the minus sign, divide by -1, get rid of that. Now there's two dots on it, equals 0. All right. And basically what we're saying here is that if we have the double dot of this r, we're talking about the acceleration of this center of mass coordinate times this total mass. All right, so this is just Newton's law, ma, right? Some forces equals mass times acceleration. Here's the mass, here's the acceleration. We're talking about the whole thing. And here it's just a central force, just the two masses. They only depend on the distance between them. There's no external force in this case. If we were to put it in, say, a uniform gravity field, we would get another term, because then our potential here would also depend on the location of the center of mass of our system. And then when that happens, then you get another force in this. Sum of forces is not equal to 0, and we have an acceleration which is not 0. We're going to see how that works with this relative displacement coordinate here, this little r. All right. So now we're going to do this equation with x is now the little r. All right. Okay. So first of all, the Lagrangian, the derivative with respect to little r is just going to be the derivative of this with respect to little r. All right. Did I do that right? I'm going to put the vector on there. Okay. All right, so that. Okay, now take the minus times derivative. And again, mu, the reduced mass, is not going to be changing with time. But first we have to take derivative with respect to little r dot. All right, just similar to what we had up here, except in this case it's mu little r dot. All right, equals 0. I'm going to divide by -1 again. And I'll write this Let's write it this way, actually. Move this to, yeah, move this to the other side, right? This one stays positive. All right. Okay, well, the negative gradient of a potential is a force, so this is actually a conservative force right here. And here's the reduced mass of our system, and here's the sort of the acceleration, if you will, of the coordinate, the space in between the two particles. All right, so this again is just a Newton's law form of an equation. Here's your sort of a force between the two particles. Reduced mass is like the mass. Oops, make that an A, not an alpha. And I should have made this one a vector equation as well. So yeah, you can see right away the parallel here. So pretty interesting stuff.